Let's start off nice and slow. We will look at an exercise where we will get better acquainted with the definition of almost sure convergence of random variables. So if we consider exercise 1.1 in the book of advanced probability, we're asked to consider a real random variable x, and then we are also asked to consider a sequence of real numbers an, and we place the assumption upon this sequence that we assume that the an tends towards 0. So this means that this sequence can behave however it behaves to begin with, but as long as n becomes large enough, the an will start to go towards 0. Then we are asked to define a sequence of random variables xn that are given as such. So x1 is a1 multiplied by x, and x2 is a2 multiplied by x, and so on and so on. So we construct some new random variables by multiplying these an's onto x. And the purpose of the exercise is to show that these new random variables that we create converge almost surely towards the deterministic value 0 as n tends to infinity. So we want to show that this is true. Before we start doing any calculations, let us just recall some of the definitions that we have. First of all, the setting in which we look at random variables. We always assume that we consider some underlying probability space with the set omega of outcomes, and it has the sigma algebra F and a probability measure P. So any outcome inside this probability space we denote with a little omega. And the way we define a real random variable x is we think of it as a mapping or a function that takes every value of omega inside the space of outcomes and maps it over to some number on the real line. So this is what x does. It takes every omega and maps it over to the real line. Now, as Ernst has said during the lectures, most of the time we don't really think about the exact construction of x. We don't think about, is x omega multiplied by 3 to the third or something like that. The thing is that we normally think of the stochastic variables x in terms of their distribution. However, when we talk about almost sure convergence, it is very, very useful to think of the underlying probability space because of the way that almost sure convergence is defined. So let us just recall the definition of almost sure convergence. Oh yes, wait, I just need to right up here, just remember that the x has to be measurable, right? It has to be FB measurable. So it is a measurable mapping. Yes. Okay, so almost sure convergence. It is very important, I think, to understand the concept of almost sure convergence from a very, very technical point of view, in the sense that it is also one of the few modes of convergence of random variables that we are able to understand in a very literal sense. So, given a sequence of random variables, given x1, x2, etc., real random variables, we say that this sequence xn converges almost surely towards some stochastic variable that we can call x or y or whatever, converges almost surely towards something. No, this x is not the x that we're looking at in the exercise. Now we're only talking about definitions. Anyways, we say that xn converges almost surely towards x if the probability of xn going towards x is 1. And what does that actually mean? It means that if we consider again the underlying probability space omega fp, now each of these xn's, x1, x2, x3, and so on, they are stochastic variables that map outcomes from omega fp to the real line. x1, x2, x3, and so on and so on. Now, when we say that the probability of this event has to be equal to 1, it means that the probability of the set of those outcomes, omega, for which xn of omega tends to x of omega, well, that set has full probability. So let's just write this up. It means if the probability of the omega for which xn of omega tends towards x of omega is equal to 1. Now, what does this mean exactly? If I take some outcome omega inside my probability space, then I can consider the sequence x1 of omega, x2 of omega, x3 of omega, and so on and so on. Now, either this sequence converges towards something as the subscript goes towards infinity, or it doesn't, right? So either it converges towards something that we can then define as x of omega, or it converges to nothing. It might be oscillating, it might blow up to infinity, it might do something weird. But either it converges to something or it converges to nothing. If we consider the set where we gather all of the omegas, where x1 and x2 and so on evaluated in that omega converges towards something, and if that set of all of these omegas has full probability measure, then we say that xn goes almost surely towards some stochastic variable x. And as I mentioned before, this definition of almost sure convergence is the definition of almost sure convergence is a very comfortable construct in the sense that, everything is just going wrong on the screen right now. I have to do a bit of damage control before we continue. Here we go. Okay, so the construction of almost sure convergence can be taken in a very literal sense, which is quite nice. And that is also what we will be doing in the next video where we solve this exercise.